Welcome to Space Science. Have we ever truly understood time, or have we only learned how to measure it? Physics can track the age of stars, slow clocks with gravity, and predict the motion of galaxies, yet time itself still refuses to reveal its deepest secret. The deeper science looks into the universe, the stranger time becomes. Tonight, Space Science follows that mystery from the largest structures in the cosmos to the smallest quantum scales, exploring one question that even modern physics still cannot fully answer. If this is the kind of deep space and science journey worth taking, please like the video, subscribe to the channel, and stay with the story. Far beyond Earth, beyond the Sun, beyond the nearest stars, the universe presents its broadest face as a field of light in motion. It appears vast, dark, and quiet, yet it carries signs of change everywhere. Galaxies do not stand still. Light does not arrive all at once. Space itself does not remain fixed. In this widest region, time first appears not as a clock on a wall or a number on a screen, but as change spread across the whole visible cosmos. Physics begins here because the largest things reveal the deepest patterns most clearly. The universe shows age, sequence, growth, and cooling on scales so large that no human event can compare with them. Even before any exact definition is attempted, time seems present in these changes, as plain as the fading warmth of an ember, and as large as the sky. The visible universe contains hundreds of billions of galaxies, and each galaxy contains stars, gas, dust, and dark matter gathered by gravity. These great systems form clusters and filaments across distances so immense that ordinary language struggles to hold them. Yet their arrangement is not random noise. It carries the imprint of a long history. Galaxies show different stages of formation and motion. Some are calm spiral systems with ordered arms. Some are dense elliptical systems filled with older stars. Some are colliding, stretching, and merging under gravity. These forms suggest that the universe has not always looked the same. It changes. It develops structure. Matter gathers, heats, shines, and settles over immense spans. In the broadest outer region, time seems almost identical to this long unfolding. One of the strongest signs of this unfolding lies in the expansion of the universe. Observations show that distant galaxies are, on average, moving away, and the more distant they are, the faster this recession appears. This does not mean that galaxies rush through a fixed emptiness in the ordinary sense. It means that space between large cosmic structures stretches. The great fabric of distance grows. When physicists describe the universe as expanding, they describe a change in the scale of space itself. This expansion offers a kind of cosmic timing. A universe that expands from a hotter, denser early state has a history that can be measured in broad outline. Present conditions carry marks of earlier conditions. The cosmos has not remained still for eternity in its current form. It has moved through stages. The most important light in this outermost region is not the light of stars, it is the cosmic microwave background, the faint afterglow of the early universe. This light fills all directions with remarkable uniformity. It is not bright to human eyes, and it does not come from a single object. It is ancient radiation released when the young universe cools enough for matter and light to separate cleanly. Before that moment, the universe remains so hot and dense that light scatters constantly and cannot travel freely over long distances. After cooling, light begins to move across space largely unhindered. That ancient light still arrives today, stretched by cosmic expansion into microwave wavelengths. It forms a nearly even bath of radiation across the sky, with tiny variations in temperature from place to place. Those tiny differences matter greatly. They reveal slight unevenness in the early universe, the seeds from which later structure grows. This afterglow acts like a background clock, though not in the mechanical sense. It does not tick. It records. It shows that the universe passes from opacity to transparency, from greater heat to lesser heat, from a simpler early state to a more structured later one. Its temperature today is very low, only a few degrees above absolute zero, and that low temperature itself is a sign of age and expansion. A hotter universe lies behind it. Observations indicate that this picture is strongly supported by measurements from multiple missions and many kinds of data. It remains uncertain what, if anything, lies before the earlier stage that present theories describe reliably. But the broad story from the early hot universe onward stands on firm ground. In this vast outer setting, time first takes shape as cooling, thinning, and expansion. Even the smoothness of the cosmic microwave background contributes to the mystery. The background is almost the same in every direction. The tiny differences are real, but the overall sameness is striking. Physics can describe this condition with great precision, yet the fact remains quietly astonishing. The universe on the larger scale begins in a state that allows clocks, stars, planets, and living beings to exist much later. At this scale, time is not yet a personal experience. It is not minutes passing in a room. It is a condition by which the whole universe changes from one overall state to another. One state follows another with lawful order. Heat drops, matter settles, structure grows. These are not opinions of observers. They are features of the world. Still, this wide view does not fully answer what time is. It shows what time does, or at least what appears with it. It allows age to be estimated for the universe as a whole. It allows earlier and later conditions to be distinguished. It allows a timeline of large events to be built from observation. Yet none of this alone explains why there is a difference between earlier and later, or why change is possible at all. The outer cosmos offers evidence of sequence, but not the final meaning of sequence. It reveals a grand order of before and after, while keeping silent about why such order exists. The mystery begins not because time is absent, but because time is everywhere in the evidence and still difficult to define. The largest universe therefore serves as the calmest starting point. It strips away the noise of daily life and presents only immense patterns. Darkness holds galaxies like scattered islands. Thin radiation fills the gaps. Distances widen. Ancient light cools. Structures gather slowly under gravity. The universe does not explain itself in words, yet its outer face speaks plainly through change. Physics reads that change and measures it with increasing care. It can say that the cosmos is not static. It can say that the visible universe has a thermal history. It can say that present conditions preserve traces of earlier ones. It can say that time, at the broadest observable scale, appears woven into expansion and history. But even here, where the evidence is widest and the patterns are cleanest, the central puzzle remains untouched at its core. Physics can measure the age of the universe far more easily than it can say what time itself truly is. Across the night sky, every visible star seems to belong to a single present. They appear together above a dark horizon, scattered across one dome, arriving at the eye in the same calm moment. Yet physics shows something quieter and stranger. No star is seen as it is now. Each one is seen by light that leaves earlier and travels across space before reaching Earth. Some of that light has crossed only a few years. Some has crossed hundreds, thousands, or millions of years in the broader universe. More distant galaxies send light that has travelled for billions of years. The sky, therefore, does not present a single time. It presents a layered record. Distance and delay turn the heavens into a visible archive, where outer space becomes a map of earlier states of matter and light. Light travels at a finite speed, very great but not infinite. Because of this, every act of seeing involves a delay. On Earth, that delay is usually too small to notice. The light from a nearby tree reaches the eye almost at once by ordinary human standards. Even sunlight, travelling across the distance between Earth and the Sun, arrives in only a few minutes. But on cosmic scales, the delay becomes the main condition of observation. A star several hundred light-years away is seen by light that leaves when events on Earth belong to a different historical age. A galaxy millions of light-years away is seen in a state older than human civilization. A galaxy billions of light-years away is seen when the universe itself is much younger. Looking outward, therefore, means looking backward. The greater the distance, the earlier the scene. This fact is not a poetic comparison. It is a direct physical consequence of how light moves. A light year is the distance light travels in 1 year, and that measure links space to time in a simple way. It allows distance itself to become a record of elapsed duration. In daily life, a road does not usually preserve the age of what lies at its end. In astronomy, distance does exactly that. The deeper the gaze into space, the deeper the gaze into the past. This sky becomes a chronology written in arrival times. Nearer objects tell a more recent story. Farther objects tell an older one. Physics uses this relation constantly. It is one of the basic reasons why the universe can be studied as a history, rather than only as a collection of objects. This historical view becomes especially clear with galaxies. Nearby galaxies often appear mature, with long-developed structures and stars of many ages. Very distant galaxies, seen by ancient light, often appear smaller, more irregular, and more active in star formation. These differences help reveal how galaxies change over cosmic time. Observations indicate that stars form more intensely during certain earlier periods of the universe than they do now on average. Black holes in galactic centers also show changing activity across cosmic history. The distant universe is therefore not only far away, it is earlier in development. Telescopes do not simply magnify remote objects. They open windows into different ages. A powerful telescope becomes, in part, a device for reading time through light. Even ordinary starlight carries this layered meaning. A star shines because matter in its core undergoes nuclear fusion, the process in which lighter atomic nuclei join to form heavier ones, releasing energy. That energy moves outward through the star and then crosses space. By the time the light arrives, the star itself may have changed. In rare cases, it may even have ceased to exist in the form being observed. A star seen at great distance may already be in a later stage unknown to the observer. This does not make the observation false, it makes it historical. Physics accepts that knowledge of the universe is always received with delay. The world does not present itself instantly. It arrives carried by signals that take time to travel. The same principle applies to more dramatic events. When astronomers observe a supernova, they witness the violent death of a star, but only when the light of that explosion finally reaches Earth. When they detect the fading glow of such an event across a galaxy, they are reading something completed long ago at its source. When they study the chemical patterns in ancient starlight, they are tracing matter that has already passed through generations of stellar birth and death. Light preserves these traces with remarkable reliability. It carries information about temperature, motion, composition, and age. A spectrum, the spread of light by wavelength, can show which elements are present and how fast an object is moving toward or away from the observer. Thus, the delayed signal is not empty. It is rich with detail. It allows the past to be examined with care. Yet this ability to see the past does not solve the nature of time. It deepens the puzzle. The sky reveals that different paths coexist in one field of view. A nearby star and a distant galaxy appear side by side, though their light begins its journey in vastly different eras. The observer gathers them in one present act of seeing, but the information within that act comes from many different moments. The heavens therefore resist any simple idea that the universe presents itself all at once. Observation itself is layered. The present contains signals from different depths of history. Physics can sort and measure these depths, but the result is unsettling in a quiet way. What seems simultaneous to human perception is built from non-simultaneous events spread across vast reaches. This also changes the meaning of astronomical maps. A map of the sky is never only a map of place. It is also a map of time. Every measured distance implies a delay. Every image is an image of what has been, not what is at this instant in some absolute sense. This is why astronomy and cosmology are inseparable from temporal reasoning. To describe the universe, physics must describe when the observed light begins its journey, how long it travels, and what conditions exist at the source when it leaves. The outer universe that first appears as a silent spread of objects now becomes a layered depth of times carried by light. Space no longer looks empty between events. It becomes the medium through which the past arrives. In this region of the subject, time is not yet a flowing inner feeling or a theoretical abstraction within deep mathematics. It is first encountered as delay, evidence, and sequence preserved by travelling light. The stars are not only distant fires, they are earlier scenes still reaching Earth. Galaxies are not only shapes in darkness, they are messages from younger cosmic ages. Physics depends on this fact at every step. It measures light, decodes it, compares signals, and builds history from what arrives. The universe becomes knowable because light does not move instantly. The same fact that limits observation also makes cosmic history visible. In that calm and distant way, the sky teaches one of the first hard lessons about time. What is seen is never simply present. It is the past still on its way. Long before physics turns to atomic clocks, equations, or curved space-time, the world offers a simpler pattern. It turns, circles, repeats, and returns. In the sky above Earth, the sun rises and sets with steady regularity. The moon grows bright, then thin, then bright again. The stars shift with the seasons. Planets move against the fixed background in wandering paths that still follow order. These motions are among the oldest sources of measured time. They do not explain what time is, but they provide recurring changes by which time can be counted. In this region of the subject, physics meets time through motion that comes back again and again, giving structure to days, months, years, and longer cycles. Earth rotates on its axis, and this turning produces the alternation of day and night. One full rotation defines the familiar daily cycle, though the exact measure depends on whether the reference is the sun or the more distant stars. Earth also travels around the sun, and that longer motion defines the year. The moon orbits Earth, and its changing position relative to Earth and the sun produces the sequence of phases that shape the lunar month. These cycles are not human inventions. They are physical motions governed by gravity and motion. Because they repeat, they become practical standards. A day can be counted by sunrise and sunset. A month can be estimated by the return of the full moon. A year can be marked by the return of seasons and the changing height of the sun in the sky. What matters here is repetition. Time seems easier to handle when some part of nature returns to a familiar state. A repeated motion allows comparison. One day can be measured against another because Earth turns again. One year can be distinguished from the next because Earth completes another orbit. This makes cyclical motion one of the first bridges between change and timekeeping. Physics later refines the bridge with great precision, but its basic idea is already present in the turning world. A process that repeats can serve as a clock. A clock, in the most general sense, is any system that passes through regular countable changes. The sky supplies such systems in abundance. The planets also play a role, though their motions are less simple to the eye. Against the fixed stars, they drift slowly and sometimes seem to reverse direction before continuing onward. This apparent reversal, called retrograde motion, does not mean the planets truly turn back in their paths. It results from the relative motions of Earth and the other planets as they orbit the Sun. Even so, the changing patterns in planetary positions become important for early astronomy and later for physics. The planets show that the heavens are not perfectly uniform lights attached to a single shell. They move in distinct ways. Their paths can be predicted, though not always by simple first impressions. This pushes time measurement toward careful observation. Repeating cycles exist, but they are nested within other cycles and sometimes seem irregular until a deeper order is found. The seasons provide another layer of regularity. Earth's axis is tilted relative to the plane of its orbit around the Sun, and this tilt changes the angle and duration of sunlight across the year. The result is the seasonal cycle. Temperature, daylight, plant growth, animal behavior, and human activity all respond to this large repeating pattern. In many societies, the year becomes real not as an abstract number, but as a return of rains, harvests, heat, and cold. Physics eventually describes these changes in terms of geometry and motion, yet the deeper point remains simple. Time, as lived and measured on Earth, first becomes stable through repeated celestial conditions. The sky offers not one cycle, but a set of interlocking ones, and these cycles anchor human life to the motion of the planet. Still, repeated motion is not the same as time itself. This distinction is easy to miss because cycles are so useful. A day is measured by one rotation, but the rotation is an event in time, not time in its essence. The moon returns to a phase, but the returning phase is only a marker. Physics can build calendars from these recurrences, compare periods, and predict future positions with great success. Yet all this concerns how time is tracked, not what time fundamentally is. The regularity of motion gives a measuring tool, not a final definition. A pendulum may swing, a planet may orbit, a quartz crystal may vibrate. These processes count intervals, but they do not by themselves explain why intervals exist or why change moves from earlier to later. This becomes clearer when cycles are examined more closely. No natural cycle is perfectly eternal or perfectly isolated. Earth's rotation changes very slightly over long spans because of tidal effects and internal dynamics. Lunar motion shifts as the Earth-Moon system evolves. Planetary orbits are stable on human timescales, but interact over far longer periods. Even the stars themselves change. A cycle that seems permanent often proves only approximately regular within a certain range. This does not make it useless. It shows that timekeeping based on nature begins with approximate repetition and grows more exact only through deeper analysis. Physics advances by finding better and more stable periodic processes, but the search itself reveals that nature offers no absolutely perfect visible clock on large scales. The history of astronomy reflects this lesson. Careful observation of the heavens leads from simple seasonal reckoning to detailed mathematical description. Repeated patterns allow prediction, and prediction strengthens the idea that the universe follows laws. In this way, regular motion becomes one of the earliest foundations of physical science itself. A lawful world is a world in which similar conditions produce similar outcomes, and in which motions can be expected to recur. Timekeeping and lawfulness therefore grow together. The repeating sky trains thought to expect order. It teaches that change need not be chaos. This is one reason cycles matter so deeply in the history of science. They do not merely mark time, they help make time measurable in a lawful universe. At this outer layer of practical time, the world seems generous. It offers motions broad enough to see and steady enough to trust. The turning Earth, the orbiting Moon, the path around the Sun, and the drifting planets all provide a framework of return. Physics receives from them its first dependable markers of duration. Yet the calm usefulness of these cycles also hides the deeper puzzle. Repetition can measure intervals, but it cannot explain why one interval succeeds another. A returning pattern can divide time into units, but it cannot say what it means for anything to endure through those units. The heavens therefore provide a beautiful convenience and a quiet limitation. They make time countable while leaving its nature unresolved. The sky turns, circles, and repeats, and from these motions human beings learn to measure. The mystery remains beneath the measurement, steady as the stars behind the wandering planets. On Earth, the broad cycles of sky and season gradually give way to smaller, more exact systems of reckoning. The sun and moon remain the oldest guides, but daily life presses inward toward finer divisions. Work, ritual, travel, planting, governance, and navigation all demand a steadier account of duration than sunrise and winter alone can provide. In this nearer region of the subject, time becomes organized by human effort. Shadows are watched, water is allowed to drip, sand is allowed to fall. Gears begin to turn, springs tighten and release. Later, electric signals and atomic transitions define intervals with extraordinary stability. Through all of this, the central pattern remains the same. A repeated physical process is selected, stabilized, compared, and used as a clock. Human time grows more precise, even while the deeper nature of time remains uncertain. The earliest practical clocks rely on visible change. A stick placed upright casts a shifting shadow as Earth rotates. From this simple fact come the sundial and the division of daylight into parts. A sundial does not generate time. It displays the changing position of the sun and turns that motion into a readable sign. It works only under suitable conditions and only with careful placement. Yet, it reveals an important principle. Timekeeping depends on stable regularity combined with a system of interpretation. The shadow itself is only a dark shape. A culture gives that shape meaning by assigning intervals, names, and uses. The movement of the world becomes a schedule. Other early devices free timekeeping partly from the sky. A water clock uses steady flow, a sand glass uses the repeated descent of grains, a candle clock uses the regular burning of wax. These devices still depend on physical conditions and often vary with temperature, material quality, or workmanship. Yet they make an important step inward. Time is now tracked by an enclosed process rather than only by the heavens above. A vessel empties, a candle shortens, a measured interval passes. These are modest inventions, but they show how human beings begin to build portable order from changing matter. A clock can now be carried into buildings, courts, ships, and workshops. Timekeeping moves closer to the rhythms of human action. Mechanical clocks transform this effort. With gears, weights, escapements, and later springs, they convert stored energy into repeated motion. The escapement is especially important. It controls the release of energy in regular steps, allowing the hands of a clock to advance at a nearly steady rate. This does not eliminate error, but it greatly improves consistency. Hours become less dependent on daylight and more available as shared public units. Towers sound bells. Cities coordinate labour and trade. Time grows more social, more disciplined, and more exact. A day is no longer only sunrise to sunset. It becomes a field divided into smaller measurable parts, available to many people at once. This precision deepens with the pendulum clock. A pendulum swings back and forth with a period that remains nearly constant for small swings under stable conditions. Because of this regularity, it becomes one of the great tools of accurate timekeeping for centuries. Yet even here, the lesson remains the same. A pendulum does not reveal the essence of time. It offers a dependable repeated motion by which intervals can be compared. When the motion is stable, the clock is useful. When temperature changes the length of the pendulum or motion is disturbed, the clock loses accuracy. Precision therefore requires both physical insight and technical control. Human time becomes more exact as matter is understood more carefully. Marine navigation gives this exactness special importance. To determine longitude at sea, navigators need accurate time carried from a known reference place. If the local position of the sun is compared with the time at a fixed meridian, east-west position can be inferred. This problem drives major advances in clockmaking. A clock aboard a ship must resist motion, humidity, temperature change, and long duration. The need to know location across oceans turns precise timekeeping from convenience into necessity. In this way, the measurement of time and the mapping of the Earth become closely linked. A well-kept clock becomes a guide through space. Later inventions continue the inward path. Quartz clocks use the regular vibration of a crystal under electric influence. Because quartz can oscillate with high stability, these clocks become common and accurate for ordinary use. Then atomic clocks carry the principle to a finer scale. They measure the frequency associated with transitions between specific energy states in atoms. An atom, under controlled conditions, provides a remarkably stable reference process. Modern definitions of the second are based on such transitions, making time measurement more precise than anything available in earlier ages. Physics can now compare clocks across continents, satellites, and laboratories with astonishing accuracy. Global systems of communication, navigation, and scientific measurement depend on this precision every day. Yet greater precision does not bring a final answer to the oldest question. It sharpens the distinction between measuring time and understanding time. A second can be defined operationally, meaning by the method used to realize it in practice. This is powerful and necessary. Science depends on clear operational definitions. Still, an operational definition tells how to reproduce a unit, not why time exists or why the world unfolds sequentially. A perfect clock, if such a thing could exist, would still be a device that tracks intervals. It would not automatically explain what an interval is in the deepest sense. The history of clocks therefore teaches a quiet philosophical lesson inside practical science. Measurement can become extremely exact while interpretation remains incomplete. Human time is also shaped by convention. Calendars divide the year in culturally organized ways. Time zones coordinate regions for communication and transport. Days begin at agreed hours. Schedules assign meaning to intervals that nature does not mark on its own. Noon once varies from town to town with the local sun. Later, standard time replaces this local variety for the sake of railways, administration, and commerce. Human society overlays physical processes with shared rules. These rules do not create duration, but they shape how duration is lived, organized, and understood. The clock becomes not only a scientific instrument but also a social framework. In this inner layer of practical experience, time appears familiar, even ordinary. It fills rooms with ticking, screens with digits, towers with bells, and cities with coordinated movement. It regulates sleep, work, travel, and memory. Physics helps build these systems with increasing exactness, selecting better periodic processes and correcting their imperfections. Still, the success of timekeeping hides the depth of the mystery. The better the clocks become, the more clearly they show that they are instruments of comparison, not sources of ultimate meaning. They reveal how reliably one process can stand in for another. They allow durations to be counted, synchronized, and exchanged. But they do not settle what time itself is beneath all clocks and conventions. On Earth, time becomes ordered with great skill. The mystery survives inside that order, quiet and untouched. Within classical physics, the outer sky, the measured day, and the crafted clock all begin to rest upon a deeper assumption. Beneath the changing motions of planets, pendulums, shadows, and tides, there seems to lie a steady background that does not itself change in character. This background is time as Isaac Newton conceives it in the classical framework. It does not depend on the motion of a clock. It does not slow, bend, or vary from place to place. It passes uniformly everywhere. Whether matter moves quickly or slowly, whether events are noticed or ignored, in this region of the subject, time is no longer approached through the visible sky or the making of instruments. It appears as an unseen foundation assumed by physical law. The world changes within time, while time itself remains untouched by the world. This idea is powerful because it gives physics a clean stage on which motion can be described. If time flows evenly for all things, then positions can be compared at one moment, then at another, and change can be measured against a universal standard. Motion becomes distance changing through time. Speed becomes the amount of distance covered during a certain interval. Acceleration becomes the change of speed over time. These definitions become clear and stable because time is treated as the same for all observers. A falling stone, an orbiting planet, and a rolling cart all belong to one common temporal order. There is no need to ask whether one clock disagrees with another in any deep physical way. Small errors of instruments may exist, but the underlying time is assumed to be one and the same. This classical picture fits ordinary experience very well. Daily life suggests that 1 hour in one place is the same kind of hour in another. A person on a moving ship does not seem to age differently from a person on shore in any noticeable way. Two events can be said to happen at the same time without obvious difficulty in most familiar situations. The world of common scales seems to support the idea of universal time. It is therefore not surprising that this view becomes deeply rooted in science. It makes prediction possible, supports mathematical clarity, and agrees closely with ordinary human intuition. Physics gains enormous strength from it. Newton expresses the idea with unusual directness. He distinguishes true time from the measures used to approximate it. A clock may gain or lose. The rotation of Earth may not be perfectly uniform over very long spans. Human systems of reckoning may vary. Yet behind all these imperfect measures there remains, in the classical view, a real and absolute time that flows uniformly by its own nature. In this way, time is separated from the devices that count it. A clock becomes a more or less successful attempt to follow an independent reality already there. This distinction matters greatly. It means physics is not merely coordinating events by convention. It is believed to be describing a real temporal order that exists whether anyone measures it or not. Space receives a similar treatment in the classical framework. It too is often taken as absolute, a fixed arena in which bodies occupy positions and move. Together, absolute space and absolute time form the quiet geometry of the Newtonian world. Matter can be pushed, pulled, accelerated, and constrained, but the stage itself remains unchanged. The laws of motion are written against this silent background. Forces act, mass resists, paths curve, time continues evenly through all of it. The strength of this picture lies in its simplicity. It allows very different physical events to be gathered into one system. The fall of an apple and the orbit of the moon become expressions of the same law. Their motions differ in scale, but both unfold in the same universal time. The success of classical mechanics makes this temporal picture seem almost unavoidable. It explains the motions of planets with impressive precision. It accounts for projectiles, tides, pendulums, and machines. It supports the rise of engineering and astronomy in forms of great practical power. For many purposes, it remains extraordinarily accurate even today. When velocities are far below the speed of light and gravitational fields are not extreme, Newtonian time works so well that its deeper limitations remain hidden. This is one reason the idea lasts so long. It does not fail in obvious ways at ordinary scales. It serves common life and much scientific work with calm reliability. Yet the very smoothness of the classical view conceals a weakness. It describes how change is measured and predicted, but it says very little about what time is beyond asserting its uniform flow. Time is treated as fundamental, but not explained. It is assumed rather than derived. One could say that classical physics gives time a job without giving it a deeper origin. It lets time order events, support motion, and carry equations forward. Yet it does not ask whether time might depend on matter, motion, or observation. In this framework, such questions scarcely arise. Time is too basic to be questioned from within the system. It is part of the system's ground. This reveals a quiet tension. The Newtonian world is elegant because it begins from fixed certainties. But a certainty placed at the foundation may escape examination. Absolute time becomes one of those certainties. It flows, but nothing in the theory explains why it flows. It is the container of sequence, but not itself the outcome of any deeper process. This is not an error in the ordinary sense. A theory is often built from primitives, basic ideas accepted at the start. Still, when later physics challenges absolute time, the challenge does not merely adjust a detail, it touches one of the deepest assumptions in the older structure. What once seems obvious begins to look like a choice made for clarity and power, not an unavoidable truth about nature. The classical view also preserves a universal present. If time is the same everywhere, then all events in the universe can, at least in principle, be assigned to one shared now. There may be practical delays in communication, but the underlying order remains common. The present extends across space as a single temporal slice. This idea fits naturally with ordinary thought. It seems almost built into perception. Yet in classical physics it becomes more than intuition. It is part of the formal structure. Every event belongs to a universal timeline, and simultaneity, the relation of happening at the same time, is simple and absolute. Within this inner foundation, physics achieves remarkable order. Time is steady, indifferent, and universal. It belongs neither to stars nor to clocks, but to the entire framework in which stars and clocks exist. This makes the world feel stable and intelligible. Events line up along one shared stream. Motion can be measured cleanly. Causes precede effects in one common order. For a long period, this picture seems not only useful but true in the deepest sense. Yet even at its strongest, it leaves the mystery intact. A perfect background may support physics, but it does not explain why there should be a background of this kind at all. Classical physics therefore carries time inward from the sky and the clock into the foundations of law, only to discover that a foundation can be firm and still remain unexplained. The calm certainty of classical time begins to weaken when physics turns from ordinary speeds to the behavior of light. In the older view, motion adds and subtracts in a simple way. If a carriage moves along a road and a person walks forward inside it, the speed relative to the ground is found by combining the two motions. This pattern seems natural because it fits common experience, yet light refuses to follow this expectation. Experiments and theory together lead to an unexpected result. The speed of light in empty space is measured to be the same for all observers in uniform motion relative to one another. This result does not sit easily inside the Newtonian picture. If the speed of light remains fixed, then time and space cannot both remain absolute. Something deeper must give way. In this region of the subject, Albert Einstein's special relativity begins to reshape time itself. Special relativity rests on two central ideas. The first is that the laws of physics take the same form for observers moving at constant speed relative to one another. The second is that the speed of light in empty space is the same for all such observers. These statements are simple to say, but their consequences are profound. If observers in different states of motion all measure the same speed of light, then measurements of distance and duration cannot remain identical for all of them. A moving observer and a stationary observer will not agree on how much time passes between events, or how much space lies between them. Their disagreement is not an error to be corrected by better instruments. It is part of the structure of nature. One of the first consequences is time dilation. This term means that a moving clock, as seen by another observer, runs more slowly than a clock at rest relative to that observer. The effect does not appear because a clock is damaged or because motion interferes mechanically with its parts. It appears for every kind of clock, whether it uses gears, atoms, light pulses, or biological processes, in special relativity. The slowing belongs not to the device alone, but to time itself as measured along that motion. If one twin were to travel at very high speed and later return, less time would pass for the travelling twin than for the one who remains at rest relative to the departure point. This result sounds strange because ordinary life never displays it clearly, yet it has been confirmed in many forms of experiment. The effect becomes easier to grasp when one remembers that a clock is any repeating physical process. Imagine a simple clock in which a pulse of light bounces between two mirrors. Each round trip marks one interval. If the clock moves sideways relative to an outside observer, the light pulse must travel a diagonal path between the mirrors from that observer's point of view. The path is longer. If the speed of light is fixed, then the longer path requires more time. The moving clock therefore appears to tick more slowly. This image does not prove everything by itself, but it offers a clear glimpse of how a fixed light speed forces time to behave differently from classical expectation. Length changes as well. Objects moving relative to an observer are measured to be shortened in the direction of motion. This is called length contraction. Again, it is not a mechanical crushing. It is a feature of measured space within the relativistic framework. Time intervals and spatial lengths shift together because they are no longer fully separate kinds of background. The older division between absolute space and absolute time begins to dissolve. Space and time become linked. A measurement of one depends partly on the state of motion of the observer making the measurement. At the heart of this change lies simultaneity. In ordinary thought, it seems obvious that two distant events either happen at the same time or they do not. Special relativity shows that this judgment depends on the observer's motion. Two flashes of light that are simultaneous for one observer may not be simultaneous for another observer moving relative to the first. Each observer uses light signals and clock synchronization to assign times to events. Because the speed of light is finite and fixed, these assignments vary with motion. There is no universal temporal grid behind them forcing all observers into one shared present. The loss of absolute simultaneity is one of the deepest shifts in modern physics. It means that the present is not a single global slice extending across the universe in the old classical way. This does not mean that anything becomes chaotic or subjective. Relativity is not a claim that truth depends on opinion. Different observers may disagree about durations, lengths, and simultaneity, but they do so according to strict mathematical rules. The laws of physics remain consistent. Cause and effect remain protected. No observer can use relativity to make an effect occur before its cause in a physically allowed way. What changes is the structure within which events are ordered and measured. Time becomes local to a path through the world rather than universal across all paths at once. Experiments support these ideas with remarkable strength. Particles moving at high speed survive longer than they would at rest, because time passes differently along their motion. Precise clocks flown on aircraft or carried on satellites show measurable differences from clocks on Earth when motion is taken into account. Systems such as global navigation satellites must correct for relativistic effects, or their position estimates drift rapidly. Special relativity is therefore not a remote speculation. It operates quietly inside technologies used every day. The theory succeeds not only as a mathematical structure, but as a description of how the world behaves. Even so, special relativity does not fully answer what time is. It changes the question. Time is no longer a universal invisible river flowing identically for all things. It becomes bound to motion, measurement, and the structure of physical law. Different observers carry different times depending on how they move. A proper time, meaning the time measured along a specific path by a clock travelling on that path, becomes a central idea. This proper time is not an illusion. It is what each clock actually records. The universe no longer offers one master clock behind all others. It offers many real clocks, each tied to a history of motion. This is both clarifying and unsettling. The theory explains many phenomena with great precision, yet it removes one of the oldest comforts in physics. There is no single tempo beating uniformly through the whole cosmos. Moving bodies do not merely occupy different positions in one shared time. They inhabit different measured durations. The old background falls away. What remains is a world in which time depends on relation and motion while still obeying exact law. Physics gains a deeper truth and loses a simpler picture. In this inner region, time becomes more real and less familiar at once. It keeps order in the universe, yet it no longer belongs equally to all observers. The mystery survives, now sharpened by discovery rather than eased by it. Once motion changes time, gravity begins to change it as well. Special relativity removes the old universal flow by linking measured duration to motion, yet it still treats gravity only indirectly. The next inward step comes when gravity itself is reconsidered. In classical physics, gravity acts as a force pulling masses across a fixed stage of space and time. In Albert Einstein's general relativity, that stage no longer remains rigid. Matter and energy influence the geometry of space-time, and that geometry guides motion. A clock near a massive body does not merely continue as before while a force acts around it. The rate of the clock changes with its position in a gravitational field. In this region of the subject, time is not only relative to motion, it is shaped by gravity. General relativity begins with a simple insight often called the equivalence principle. The effects of gravity and acceleration can look the same in a small enough region. A person in a closed elevator rising with steady acceleration feels weight much, as a person standing on Earth feels weight. A beam of light crossing the elevator appears to bend relative to the floor, not because light changes its own nature, but because the frame itself accelerates during the crossing. Einstein takes this likeness seriously and builds from it a new description of gravity. Instead of treating gravity as a force in the old sense, he describes it as curvature in space-time. Massive objects alter the geometry around them, and bodies move along the straightest available paths within that curved geometry. This geometrical change has direct consequences for time. A clock deeper in a gravitational field runs more slowly than a clock farther away from the gravitating mass. This effect is called gravitational time dilation. Near Earth, the effect is small but measurable. Near a neutron star or black hole, it becomes dramatic. The slowing does not arise because gravity physically damages a clock or makes its parts drag. It affects all clocks equally, whether they use pendulums, quartz, atoms, or biological processes. The difference lies in time itself as measured at different locations in curved space-time. Two clocks placed at different heights above Earth and later compared will not agree exactly. The one lower down, closer to Earth's mass, will have experienced slightly less elapsed time. This can be understood in a limited way through energy and light. If light climbs away from a massive body, its frequency shifts. A clock based on regular oscillations of light or atomic transitions is linked to frequency, so the change hints at why rates differ across gravitational conditions. But the deeper explanation belongs to the structure of space-time itself. General relativity assigns intervals of space and time according to geometry, and that geometry is not flat when mass and energy are present. The old hope for a single universal time becomes still more distant. Not only does motion matter, location in a gravitational field matters too. Earth quietly demonstrates this every day. A satellite in orbit experiences different timing conditions from a clock on the ground. Its speed tends to slow its rate through special relativity, while its higher position in Earth's gravitational field tends to speed it up relative to clocks lower down through general relativity. Both effects must be taken into account in systems that depend on accurate timing, such as global navigation satellites. If the corrections were ignored, errors in position would grow quickly. This is one of the clearest practical signs that relativistic time is not an abstract curiosity. Clocks in different gravitational settings truly diverge. The world of mountains, valleys, aircraft, and orbiting machines already belongs to curved time. the effect becomes more striking near denser objects. A white dwarf, a neutron star, or a black hole compresses mass into a much smaller region, and the curvature near such bodies is far stronger. Light escaping from their vicinity is strongly shifted. Clocks near them run much more slowly relative to clocks far away. Around a black hole, general relativity predicts extreme differences in elapsed time between regions. An observer remaining far from the black hole and an observer moving near it may later compare histories that contain very different amounts of experience duration. These predictions are grounded in the theory and in indirect observations of strong gravitational environments. Still, some details near the deepest regions, especially at singularities where the mathematical description breaks down, remain uncertain. Present theory describes many strong gravity effects very well, but it does not yet provide a complete account of the innermost extremes. General relativity also changes the meaning of free fall. In classical thought, a falling body is pulled by gravity. In Einstein's view, a freely falling body follows the natural geometry of space-time. It is not resisting a force in the same way a body resting on the ground does. The ground prevents the body from following its free path, and that prevention is part of what is felt as weight. This shift matters because it shows that time and motion are not merely happening inside a pre-existing container. The container itself has become dynamic. Geometry responds to matter and energy. Time is woven into that geometry, so time becomes part of what the universe builds rather than merely what it uses. Even with this deeper view, an ordinary intuition remains difficult to release. It still feels natural to imagine that one true time should exist somewhere underneath all these differences. Yet general relativity gives no sign of such a hidden master clock. Instead, it offers local times attached to world lines, the path that bodies and signals trace through space-time. Each clock measures the proper time along its own world line. Geometry determines how much time accumulates along different paths, just as it determines distances and trajectories. The universe contains many real times measured by many real clocks, and their differences are not defects. They are part of the physical structure. This brings both clarity and unease. Gravity, once thought to be a pull across space, now shapes the very rate at which time passes. The higher clock and the lower clock are not simply mismatched instruments. They inhabit different temporal conditions. Matter does not only move through time. Matter helps determine time's geometry. Physics thereby moves inward from motion to gravitation and finds time becoming even less absolute than before. Yet the theory remains extraordinarily precise. Light bends near the sun. Mercury's orbit shifts in just the measured way. Gravitational waves travel across space from merging massive bodies. Time dilation appears in clocks on Earth and above it. The theory works with great success. Still, success in prediction is not the same as final understanding. General relativity explains how gravity shapes time, but it does not settle why time should be part of a curved geometry at all, nor why this geometry is lived as a flowing present by conscious beings. It gives an elegant framework in which durations differ from place to place and path to path. It replaces the old silent background with a responsive structure. In doing so, it deepens the mystery. Time no longer seems like an invisible river. It resembles a feature of the universe's form, capable of stretching, slowing, and differing under gravity. The closer physics comes to the structure beneath ordinary appearance, the less familiar time becomes. Gravity does not merely act within time. Gravity shapes time, and time remains unresolved within that shaping. As motion and gravity both alter the rate of clocks, an older idea begins to fade almost completely. That idea is the universal now, a single present moment spread evenly across the whole universe. In ordinary life, this shared present feels obvious. A person points to the sky, the room, the street, and assumes that all things existing at this moment belong to one common slice of reality. Distance seems irrelevant to the fact of simultaneity. Two events either happen together or they do not. Yet modern physics steadily removes this comfort. Once the speed of light is finite and fixed for all observers, and once time depends on motion and gravity, the notion of one present valid everywhere becomes difficult to preserve. In this region of the subject, time loses its universal now. The key idea is simultaneity, the relation between events said to occur at the same time. In classical physics, simultaneity seems simple. If two lamps flash in distant places and a universal clock stands behind all motion, then the flashes either occur at the same moment or at different moments, regardless of who observes them. Special relativity changes this entirely, because light takes time to travel, and because different observers move relative to one another. The assignment of time to distant events depends on the observer's frame of motion. What one observer judges simultaneous, another may judge not simultaneous. This does not arise from confusion, delay in human reaction, or faulty equipment. It arises from the physical structure of space and time. A familiar thought experiment helps make the point clear. Imagine two flashes striking the ends of a long train. An observer standing midway along the track sees the flashes arrive together and concludes that the events are simultaneous. Another observer sitting midway inside the moving train also receives light from the two flashes, but because the train moves during the travel of the light, the order and timing of arrival differ in a way that changes the judgment of simultaneity. When the situation is analysed with the rules of relativity, both observers are correct within their own frames. The disagreement is not about appearance hiding one true answer. The disagreement belongs to the structure of the measurements themselves. This is one of the hardest ideas to accept because human intuition is strongly local. Nearby events seem easy to place inside one shared present, because light travel times are tiny at ordinary distances and speeds. In daily life, the differences are too small to notice. Human beings therefore grow up inside a world where simultaneity appears universal. Physics reveals that this appearance is approximate. It works well on ordinary scales. Just as flat ground seems truly flat over a short field while Earth as a whole is curved, the deeper structure becomes visible only when the conditions are broad enough, fast enough, or precise enough. The loss of universal simultaneity has major consequences. It means there is no single cosmic present slicing across the universe in a way that all observers must accept. Two distant events that are present together for one observer may belong to different times for another observer moving differently or situated differently in a gravitational field. A present at one place does not automatically define a universal present everywhere else. Physics can still assign coordinates to events and compare them consistently, but the older sense of one shared now dissolves. The universe keeps order without requiring a single common present. General relativity deepens this further. In curved space-time, where gravity shapes geometry, even the attempt to define a global time across all regions becomes more limited. In some settings, especially in strong gravitational fields or across very large cosmic structures, there may be useful local definitions of time and simultaneity, but no simple universal one. Space and time are coordinated by geometry, matter, and motion together. The further physics moves from local experience, the less support it finds for a single worldwide present. Time becomes something assigned locally, compared carefully, and never assumed to spread identically across all places. This does not mean that the universe falls into disorder. Causality remains intact. Causes still precede effects in ways allowed by the structure of space-time. Light cones, the boundaries traced by the possible paths of light through space-time, preserve this order. Events that can influence one another must lie within the proper causal relation. Events too distant from one another for any light signal or physical influence to connect them quickly enough may have no single agreed temporal order for all observers. This is not a failure of law, it is the law. Nature preserves causal structure without preserving a universal present. The result feels strange because the present holds great weight in human experience. Conscious life seems to unfold in a moving now. Perception gathers sounds, sights, and touch into a current moment. Memory holds what has just passed, while expectation faces what has not yet come. From this inner life, it is easy to imagine that physics should discover a matching universal present in the outer world. Instead, it finds no such feature in its most successful theories of motion and gravity. The present that feels immediate and central to experience does not appear as a single privileged layer in relativistic physics. What appears fundamental in experience becomes difficult to locate in theory. This gap between experience and theory is one reason the mystery of time remains so persistent. Physics can describe how clocks behave, how signals travel, how observers assign coordinates, and how space-time preserves causal order. Yet when it comes to the felt division between past, present, and future, the theory offers no universal present to mirror common intuition. One may still speak of the present locally, meaning here and now along a particular world line, but that local now does not spread cleanly across the cosmos. It belongs to a place and a path, not to all existence at once. At this stage, time becomes thinner as a common medium. It no longer serves as a universal backdrop through which everything passes together. It becomes a structure of relations between events, observers, clocks, signals, and geometry. What survives is not the old now, but lawful comparison. Physics keeps what can be measured and related. It lets go of what cannot be made universal. This is a profound inward turn. Earlier sections show time through cosmic history, travelling light, repeated cycles, precise clocks, classical foundations, motion, and gravity. Here those lessons converge in a quiet but decisive loss. The universe no longer appears to carry one common present for all things. And yet daily life continues as before. People still speak of today, this hour, this moment. These words remain useful because local life is built from local time. Within the narrow band of ordinary experience, the differences between observers are tiny, and the world seems to share one present well enough. Physics does not deny this convenience. It places it in context. The present of common life is real as a practical local feature, but not as a universal layer of reality. In this inner region, time becomes more exact and less intuitive at once. The now remains vivid in experience even as it fades from the deepest physical description. What disappears is not order, but the old simplicity that once seemed to make time obvious. Once the universal present has fallen away, another possibility comes quietly into view. If different observers divide distant events into past, present, and future in different ways, perhaps the universe itself does not privilege one moving present at all. Perhaps all events simply belong to one four-dimensional structure, ordered by relations in space-time rather than by a single cosmic flow. This idea is often called the block universe view, in this region of the subject, time is no longer treated as a river carrying the world forward. It is treated as part of the total shape of reality, where events occupy positions in space-time much as places occupy positions in space. The result is one of the most unsettling and persistent interpretations in modern physics. The starting point for this view is the union of space and time into space-time. In relativity, an event is something that happens at a particular place and time. A person standing still for 1 hour traces a path through space-time, even while remaining in one location in space. A planet orbiting a star traces a longer and more complex path. A beam of light traces another kind of path, constrained by the fixed speed of light. Physics describes these paths and the intervals between events with extraordinary success. Once this structure is taken seriously, the temptation grows to think of the whole network of events as equally part of reality. Past events are not erased from the structure. Future events are not absent from it in the way ordinary intuition suggests. They may simply occupy other regions of the whole. In the block view, space-time resembles a complete geometric entity. A mountain range does not need one peak to become real before another peak. The whole range exists as one structure, even though a traveller experiences it only by moving step by step. In a similar way, the block universe treats all events in space-time as belonging to one total arrangement. A human being experiences life sequentially, moment by moment, but the underlying physical reality may contain the full path at once. Birth, childhood, maturity, and death would then be different regions along one world line, all equally part of the structure, though not equally present to consciousness. The flow would belong to experience, not necessarily to the deepest external description. This interpretation gains strength from relativity, because relativity gives no universal present that could mark one privileged layer as the only fully real one. If there is no single cosmic now, then the distinction between what exists now and what does not yet exist becomes harder to define in a universal physical way. The block view answers this difficulty by removing the privilege of the present altogether. Past, present, and future become relational or perspectival categories tied to particular observers and particular locations in space-time. The physics keeps the full structure and does not require one moving slice to pass through it. There is a certain calm logic to this. Relativity already asks observers to accept that durations differ, simultaneity differs, and local clocks accumulate time along their own paths. The block universe gathers these lessons and extends them into an ontological picture, meaning a picture about what is real. It says that physics describes a world of events laid out in space-time, not a world being created anew at each advancing instant. What changes is not the structure itself, but the location of conscious awareness within it. If awareness can be spoken of in such a way at all, this last step reaches beyond strict measurement and enters interpretation, yet it is tightly connected to the structure that relativity reveals. Still, the block view is not forced beyond all dispute. Physics describes relations among events with great precision, but whether this description requires a block ontology remains debated. Some physicists and philosophers regard the block universe as the most natural reading of relativity. Others hold that the equations may be compatible with a deeper reality in which becoming, passage, or an objective presence survives in some form not yet fully captured. Observations indicate that relativity works with exceptional accuracy in its domain. It remains uncertain whether its most austere interpretation must be accepted as the final picture of time. The mathematics is powerful. The metaphysical conclusion remains contested. One reason for resistance is the apparent passage of time in experience. Human life does not feel like a static geometry. It feels dynamic. Sounds arrive, thoughts unfold, decisions seem open until made, and memory points backward while anticipation points forward. The world seems to come into being as the present advances. The block universe appears to deny this directly. If all events are equally real, then change itself can seem downgraded to a matter of perspective. A leaf falling from a tree, a star exploding, a child growing older, all become fixed features of the whole structure. The sense of happening becomes difficult to place. Defenders of the block view answer that change is not denied, it is redescribed. Change means differences between states at different locations along a world line or across space-time. A tree is green in one region, bare in another. A person is young at one event, old at another. The full structure contains these differences. What it may not contain is a physically fundamental moving present sweeping across them. From this perspective, the world does include change, but not passage in the deep intuitive sense. Passage is replaced by ordered variation across the block. Whether this counts as preserving change or emptying it of its deepest meaning is one of the central tensions in the philosophy of time. The block view also affects ideas of causation, freedom, and openness. If future events are as real as past ones within space-time, then the future may seem fixed. This can create the impression that novelty and genuine becoming vanish. Physics itself is careful here. The equations describe relations and lawful evolution, but questions about determinism depend on the theory, the initial conditions, and the interpretation, quantum physics, which lies deeper inward in this exploration, complicates the issue further. For now, it is enough to see that the block picture sharpens the mystery by presenting a universe that is coherent and measurable, yet at odds with ordinary temporal experience. In this inner region, time risks losing its flow entirely. The cosmos becomes a complete space-time arrangement in which every event has its place. World lines stretch through it. Light cones define causal order. Proper time marks durations along paths. Nothing in the geometry itself seems to require a universal moving now. Physics can operate within this picture with great success, yet the cost is substantial. The vivid human distinction between what has happened, what is happening, and what has not yet happened no longer appears fundamental. It becomes local, experiential, or perhaps emergent from something deeper. The block universe therefore stands as one of the starkest outcomes of modern thinking about time. It grows naturally from relativity, from the loss of universal simultaneity, and from the union of space with time in one mathematical structure. It offers order without flow, completeness without becoming, and law without a privileged present. Whether this is the last word remains unknown, but within the current path inward, it marks a decisive moment. Physics can describe the world with remarkable power, while leaving open the question of whether the felt passage of time belongs to reality itself or to the way conscious beings move through an already laid out space-time whole. Inside the great structure of space-time where motion alters duration and gravity bends the rate of clocks, there remains one feature of ordinary life that stands out with unusual force. Broken glass does not leap from the floor and reassemble into a cup. Smoke spreads through a room and does not gather itself back into the flame. Warm tea left on a table cools toward the surrounding air and does not spontaneously grow hotter while the room grows colder. The world displays direction. Whatever time may be in its deepest essence, experience and physical process alike reveal a strong difference between one way and the other. In this region of the subject, physics turns from geometry to thermodynamics and finds the most familiar direction of time in entropy. Entropy is a technical term, but its core meaning can be stated simply. It measures how many microscopic arrangements correspond to the same larger visible condition. A neat deck of cards has fewer arrangements that count as neat than a shuffled deck has arrangements that count as mixed. A gas confined to one corner of a box can exist in relatively few detailed arrangements, compared with a gas spread evenly through the whole box. A melted ice cube in warm water corresponds to many more microscopic arrangements than a sharply separated cube of ice in a glass. Entropy, therefore, tends to be higher in conditions that are more spread out, more mixed, and more statistically common. In ordinary physical systems left to themselves, entropy tends to increase. This tendency gives time an arrow. An arrow of time means a preferred direction from earlier to later. Thermodynamics, the branch of physics that studies heat, work, temperature, and energy transfer, contains this direction at its center. The second law of thermodynamics states, in broad form, that the total entropy of an isolated system does not decrease over time. It may stay constant in ideal reversible cases, but in everyday processes it usually rises. Heat flows from warmer places to cooler ones until a more even distribution is reached. Differences smooth out, ordered concentrations disperse, energy becomes less available for producing organized change, even though total energy remains conserved. This one-way drift is among the strongest physical reasons time feels directional in ordinary life. The remarkable point is that many basic microscopic laws do not obviously prefer one-time direction. At the level of simple collisions between particles, the equations often work nearly as well forward as backward. If the velocities of all particles in a simple system could be exactly reversed, the laws would in many cases allow the system to retrace its path. Yet large systems do not behave this way in practice. The reason lies in probability. There are vastly more disordered microscopic arrangements than ordered ones. A system therefore evolves from less probable large-scale states toward more probable ones, not because the laws forbid the reverse absolutely in every tiny detail, but because the reverse would require extraordinary precision and is overwhelmingly unlikely. A drop of ink in water offers a clear example. At first, the ink occupies a compact region. Over time, the molecules spread through random motion until the color becomes diffuse. Nothing in the microscopic laws singles out spreading as fundamentally permitted and gathering as fundamentally forbidden in a simple absolute sense. But the number of molecular arrangements corresponding to a spread-out state is enormously greater than the number corresponding to a compact drop. The system therefore moves toward the overwhelmingly more probable condition. Entropy increases. Time, in this practical and statistical sense, points from concentration toward dispersal. This helps explain why the world seems full of irreversible processes. A cracked stone remains cracked. A perfume released into air diffuses through a room. A hot object cools in a colder environment. In each case, the reverse process is not impossible in the barest logical sense under microscopic law, but it is so improbable for large systems that it never appears in ordinary experience. Thermodynamic irreversibility arises from the behavior of enormous numbers of particles. The arrow does not come from one atom carrying a tiny sign that says future. It comes from the collective behavior of matter under statistical law. Still, this explanation brings another layer of mystery. If entropy tends to increase, that tendency depends on starting from a lower entropy condition. The arrow of time in thermodynamics therefore points back toward the question of why the universe begins in such an unusually low entropy state. The early universe is hot and nearly uniform on large scales, which might seem at first glance to be a high entropy condition. Yet when gravity is included, the issue becomes subtler. A smooth distribution of matter under gravity can represent lower entropy than a later universe filled with stars, galaxies, black holes, and complex structure. The exact accounting is deep and still studied carefully, but the broad point is clear. The thermodynamic arrow requires a special beginning. Without such a beginning, entropy would not have room to rise in the way observed. Thus, the arrow of time is not fully explained by saying that entropy increases. That statement is true and powerful, but it shifts the deepest question one step further inward. Why is the universe arranged so that entropy can increase from earlier states to later ones? Why does the cosmos begin in a condition that allows stars to form, heat to flow, chemistry to unfold, and life to emerge against a background of growing disorder? Observations indicate that the universe does in fact possess this history. It remains uncertain why the initial condition has exactly the character it does. Physics describes the arrow with growing precision, yet the origin of the arrow remains tied to the origin of cosmic order. Entropy also changes the meaning of order and disorder in subtle ways. It does not simply mean tidy versus messy in the everyday sense. A crystal can be highly ordered at the microscopic level, and a gas can look featureless while holding high entropy, because so many microscopic arrangements produce the same visible condition. The concept is about counting possibilities beneath appearances. A low entropy state is one that can be realized in relatively few microscopic ways. A high entropy state can be realized in many. The future, in ordinary thermodynamic terms, is the direction toward the more numerous possibilities. The past is the direction toward the fewer. This is why records, structures, and organized differences are precious and fragile. They occupy special conditions that easily give way to more common ones. In living systems, local order can grow, but only by exporting entropy elsewhere. A plant builds complex structure by using sunlight and releasing heat. An animal maintains its body by consuming low-entropy energy sources and contributing to greater entropy in its surroundings. Life does not violate the second law. It depends on larger flows that satisfy it. This is important because it shows that increasing entropy does not mean all local structure must vanish at once. Complex forms can arise and persist for a time within broader one-way processes. The arrow of time, therefore, does not erase pattern. It permits pattern within an overall drift. At this stage of the inward path, time acquires direction in the most familiar domain of physical process. The block universe may suggest a complete structure without privileged flow, and relativity may remove the universal present. Yet thermodynamics restores something that feels close to lived experience. There is a difference between before and after in the cooling cup, the spreading smoke, the aging body, and the fading star. Physics can name this difference with entropy and support it with powerful law. Yet even here the mystery is not closed. The arrow of time is described, measured, and seen everywhere in ordinary change, but its deepest root still points back to the special character of the universe as a whole. Entropy gives time a direction. It does not finally tell why there is a direction to give. Once entropy gives physical processes a clear direction, another question settles into view with unusual stillness. Why does the past leave traces while the future does not? Why do rocks preserve fossils? Why do photographs preserve light from earlier moments? Why does the brain hold memory of what has happened? And why does no equal store of evidence arrive from what has not yet occurred? In this region of the subject, time is examined through records. The world is full of marks left behind. Tree rings carry seasons within wood. Layers of ice hold old air within frozen depth. Craters preserve impacts. Written pages hold thought after the hand has moved on. Even the faint glow of distant galaxies is a record. Light arriving late from earlier states of matter. The universe seems built to keep traces of the past. It does not seem built to keep traces of the future. A record is any present structure that depends in a reliable way on an earlier event. A footprint in wet ground is a record of pressure and motion. A scar in stone is a record of fracture. The pattern of ashes in a fire pit is a record of burning. Memory in the human brain is a biological record formed through changes in neural connections. None of these records is magical. Each is a physical consequence of interaction. Matter changes, and the change remains after the event that produces it. The present therefore contains information about what has already happened. Physics can often decode these traces and reconstruct earlier states with considerable success. Geology reads ancient climates in rock. Astronomy reads past stellar processes in light and chemical abundance. Biology reads ancestry and genetic sequences. The world is legible because events leave marks. This legibility is closely linked to entropy. To create a record, a system must undergo an irreversible or effectively irreversible change. A camera sensor changes when light strikes it. Clay deforms under a seal. A brain changes through experience. In each case, physical processes move from one state to another and leave behind a stable difference. Stable here means not perfectly eternal, but persistent enough to be read later. Such persistence depends on the broader thermodynamic environment. A record forms because energy flows, matter reorganizes, and the resulting state is more probable to retain than to spontaneously erase itself. The formation of records therefore belongs to the same one-way character that governs heat flow and mixing. A record is not just information. It is information embedded in a thermodynamic arrow. This explains why memory points backward. The brain is a physical system. It stores information by changing its structure through interaction with earlier events. It cannot remember the future in the same physical sense, because the future has not yet left such traces in the present state of the brain. What is called anticipation or prediction is different. It is an inference built from past records and present conditions, not a memory of future events themselves. Physics therefore gives a clean distinction. Memory is asymmetrical because record formation is asymmetrical. The mind is not standing outside time and looking both ways equally. It is a material process inside a world where records accumulate from earlier to later. The same asymmetry appears outside living beings. Light from a distant star reaches Earth after traveling for years or millions of years. That light carries information about the earlier state of the star. A fossil holds the mineralized shape of a once living body. Sediment layers store changing environments one above another. These are all records. They are valuable precisely because they survive. They survive because the world contains many processes that preserve earlier influences in stable form. Physics and the historical sciences rely on this fact constantly. Without records, there would be no astronomy in its historical sense, no geology, no archaeology, no biography, and no memory-rich consciousness. The past would leave no accessible structure behind. Yet the existence of records does not merely reflect the arrow of time, it intensifies it. The world feels directional partly because the present is crowded with evidence of earlier states. The present contains ruins, photographs, scars, echoes, cooling remnants, and memories. These structures all point one way. They indicate what has happened. There is no corresponding abundance of structures in the present that function as direct records of what has not yet happened. This one-sidedness gives temporal experience much of its shape. A person wakes inside a room already full of traces. Dust has settled, objects have aged. The body itself carries marks of earlier days. The world feels like it comes from somewhere because it literally bears the signs of where it has been. This relation between records and irreversibility can be seen even in simple devices. A thermometer records a temperature by reaching thermal equilibrium and displaying a value. A detector records a particle by registering an interaction. A notebook records a thought by preserving ink on paper. In every case, recording requires physical change. Once the mark is made, the system and often the surrounding world have moved to a new state. To erase the record perfectly and restore every microscopic detail would require an extraordinary reversal of countless interactions. In practice, the process is one way. Records therefore accumulate in the same temporal direction in which entropy tends to increase. There is also a deeper point. Records do not merely sit in time. They help define the practical distinction between past and future. The past is the domain from which records are available. The future is the domain toward which records are absent and only projections are possible. This does not mean the future is unreal. It means that knowledge of it is structurally different. Physics can predict, sometimes with great accuracy, but prediction is not retrieval. It uses law and present data to infer what is likely or necessary later. By contrast, knowledge of the past often comes by reading what earlier events imprint into the present. The asymmetry between record and prediction contributes to the asymmetry between memory and expectation, evidence and forecast. Still, records do not solve the mystery at the deepest level. They depend on the arrow of time rather than creating it from nothing. A footprint exists because matter deforms irreversibly enough to preserve shape. Memory exists because neural tissue changes and retains patterns. Cosmic background radiation exists because the early universe passes through conditions that let light travel freely thereafter, in each case. Records arise within a world already structured by one-way processes and special initial conditions. To explain records fully is therefore to return again to entropy, probability, and the low entropy past. The chain of explanation keeps moving inward. There is also uncertainty at the frontiers. In some areas of physics, especially quantum measurement and information are involved. The exact relation between records, irreversibility, and fundamental law remains an active subject of study. Observations indicate that record formation is central to how the classical world of stable outcomes emerges from underlying physical processes. It remains uncertain whether irreversibility is fully fundamental, or whether some aspects of it emerge from deeper descriptions that are themselves more symmetric. Even here, the lived fact remains clear. The world is thick with traces of what has already happened. In this inner region, time becomes tangible through marks left behind. The cosmos is no longer only expanding, shining, orbiting, or curving. It is storing. The present holds the worn edges of earlier events in matter, light, and mind. Physics can often read those edges with remarkable power, reconstruct and vanish stars, extinct creatures, and ancient climates. Yet every recovered story depends on the same quiet asymmetry. The past deposits, the future does not. Memory, evidence, and record all lean in one direction. They make time feel one way because the world itself preserves one-way traces. And still, the mystery remains. Physics can describe how records form and why they align with entropy. But the deeper origin of that alignment still reaches beyond the record itself, inward toward more basic questions about law, information, and the structure of reality. Beneath the world of stable records, drifting heat, and familiar objects lies a smaller domain where matter and radiation behave in ways that resist ordinary expectation. Here particles do not always follow sharply defined paths in the classical sense. Light can behave like a wave and also arrive in localized detections. Atoms emit and absorb energy in discrete amounts. Outcomes can be predicted with extraordinary accuracy in the aggregate, while remaining probabilistic in individual events. In this region of the subject, physics enters quantum theory and finds that time is both present and strangely unsettled. The theory works with remarkable success, yet its treatment of time leaves deep questions still open. Quantum physics begins from the failure of classical ideas at very small scales. Classical mechanics can describe planets, falling stones, and pendulums with great power, but it cannot explain the stability of atoms, the spectral lines of elements, or the behavior of radiation in many microscopic experiments. Quantum theory answers these problems by introducing a new mathematical description. Instead of assigning a particle a fully classical trajectory at all times, the theory uses a quantum state, often represented by a wave function, which encodes the probabilities of different measurement outcomes. This wave-like description evolves smoothly according to precise laws, yet when a measurement is made, a definite outcome appears. The relation between these two aspects of the theory is one of the central sources of the mystery. Time enters quantum theory in a curious way. In the standard formulation of non-relativistic quantum mechanics, time is treated as an external parameter. It is not usually represented as an operator in the same way position or momentum are. The quantum state changes with time according to the Schrödinger equation, which gives a continuous and deterministic evolution of the state between measurements. In this sense, time acts as the background variable against which the state evolves. This is striking because relativity already teaches that time is not an absolute backdrop, independent of physical conditions. Yet in ordinary quantum theory, time often reappears as if it were just that, a fixed parameter supplied from outside the system. The theory succeeds extremely well in practice, but this formal role of time stands in tension with the relativistic picture. Quantum events themselves often seem to sharpen the problem of temporal order. A radioactive atom may decay at one moment rather than another, and the theory can assign a probability for decay over time. But it does not, in ordinary interpretation, specify a hidden clock telling exactly when the decay must occur. A photon may be detected at one location rather than another according to a probability distribution. Interference patterns arise when many events are collected, yet each detection appears as a single localized occurrence. The theory therefore gives precise statistical structure, while leaving individual outcomes uncertain until measurement. Time remains present in the equations, but the unfolding of actual events acquires a probabilistic character unlike the old classical picture. This probabilistic nature does not mean that quantum theory is vague or incomplete in the practical sense. It is among the most accurate theories ever developed. Its predictions for atomic spectra, semiconductor behavior, chemical bonding, lasers, and many other phenomena match observation to extraordinary precision. The uncertainty lies not in its success, but in its interpretation. What exactly happens when a quantum possibility becomes a definite recorded event? Does the wave function represent physical reality directly, or only information about possible outcomes? Does a measurement produce a special kind of change, sometimes called collapse, or does the full quantum state continue in a larger description that includes the measuring device? These questions matter for time because measurement seems to introduce a difference between before and after. Before measurement, multiple outcomes may be represented in superposition, meaning a combination of possible states. After measurement, one definite result is recorded. The transition carries a temporal asymmetry that remains debated. Superposition is a central quantum idea. It means that a system can be described by a combination of possible states until interaction or measurement yields a definite observed result. This does not mean a particle is simply half-decided in an everyday sense. It means the mathematical structure of the theory allows different possible outcomes to combine and interfere. Such interference has been confirmed in countless experiments. Yet once a stable record exists, one outcome is found. The world of records discussed earlier therefore seems to emerge from a deeper layer in which definite classical alternatives are not always fixed in advance in the familiar way. Time at this scale is tied not only to evolution, but also to the appearance of outcomes. Quantum entanglement adds another layer. When particles interact in certain ways, their properties can become correlated such that the quantum state of the combined system cannot be reduced to separate independent states for each part. Measurements on entangled systems reveal correlations stronger than classical local hidden variable theories can account for. Experiments support these quantum predictions decisively. Yet entanglement does not permit signals to travel faster than light in a way that would violate relativity. Causal order remains protected. Still, the existence of such non-classical correlations complicates any simple picture of time as a chain of localized independent events unfolding one by one. Quantum systems can carry relations that do not fit neatly into classical temporal intuition. At the same time, many core quantum equations are reversible in their mathematical form. Like several classical microscopic laws, they often do not contain an obvious built-in arrow pointing from past to future. The Schrödinger evolution itself is time-symmetric in a broad sense, yet measurements, records, and macroscopic irreversibility plainly display asymmetry. This gap has led physicists to study decoherence, the process by which quantum systems interacting with their environments lose the observable interference effects that characterize delicate superpositions. Decoherence helps explain why definite classical behavior emerges so effectively in ordinary conditions. It shows how entanglement with the environment can disperse phase relations into inaccessible degrees of freedom, making certain outcomes stable and record-like. This provides a powerful account of why the classical world appears. It remains uncertain whether decoherence alone fully solves the measurement problem or only shifts part of it into a broader framework. Thus, quantum theory places time in an unstable position. On one hand, the equations use time as a parameter and track the evolution of quantum states with extraordinary success. On the other hand, the appearance of definite events, records, and classical histories introduces asymmetries that are not trivial to derive from the underlying formalism alone. The theory seems to need time to describe change. Yet it also seems to leave unexplained how temporal definiteness emerges from quantum possibility. Physics can calculate astonishingly well. Interpretation remains divided. This is why the quantum domain feels so inward and so unresolved. Earlier regions reveal time through cosmic expansion, light travel, cycles, clocks, relativity, entropy, and records. Here all of those clear structures meet a world in which possibility itself becomes fundamental in the description. A particle is not always simply here or there in the old sense before measurement. An atom does not always carry a classically determined moment of decay. A quantum state unfolds according to law. Yet the relation between lawful evolution and actual occurrence remains debated. Time is in the theory and still not fully at rest within it. In this region, physics achieves some of its finest predictive triumphs while exposing one of its deepest conceptual fractures. Quantum theory shows that the microscopic world can be described with extraordinary precision, but it does not give a universally accepted account of how temporal order, definite outcomes, and experienced reality arise from its own formal structure. Observations indicate that the quantum framework is profoundly successful. It remains uncertain exactly what this success implies about the ultimate nature of time. At the inward edge of microscopic physics, time continues to function, yet its meaning grows thinner, more conditional, and more mysterious than ever. As quantum theory reaches extraordinary precision, the instruments used to count time also move inward toward the smallest stable processes known. The old sky, the turning earth, the swinging pendulum, and the vibrating quartz crystal all give way to finer standards. Modern clocks no longer depend on visible motion across large distances. They depend on regular transitions within atoms and, in newer designs, on even higher frequency transitions involving light. These clocks do not solve the mystery of time, but they sharpen it. In this region of the subject, physics approaches the quantum edge of measurement and finds that time can be counted with astonishing success even while its underlying nature remains unsettled. An atomic clock works by using a natural frequency associated with the specific transition between energy states in an atom. An energy state is a permitted condition of the atom, not a continuous range chosen at will. When the atom changes between these states, it can absorb or emit radiation at a highly specific frequency. This frequency is stable enough under controlled conditions to serve as a reference for measuring intervals. Modern definitions of the second rely on such atomic transitions. The clock does not watch hands go around a face. It counts an immense number of microscopic oscillations and converts them into a unit that can be shared across laboratories, continents, satellites, and communication systems. The stability of these clocks is one of the great achievements of modern experimental physics. Small disturbances from magnetic fields, temperature changes, motion, and gravity must be controlled or corrected. Atoms may be cooled with laser techniques so that thermal motion does less to blur the frequency. Traps and vacuum systems hold them under carefully prepared conditions. Electronic systems compare the atomic reference with counting circuits that can keep track of vast numbers of oscillations. The goal is not merely to build a useful device, but to isolate a process so regular that it becomes dependable standard against which other changes can be measured. Precision grows because the microscopic world, though conceptually strange, provides repeatable structure when handled with care. Optical clocks take this effort further. Instead of relying on lower frequency microwave transitions, they use transitions associated with optical frequencies, meaning frequencies of light. Because these oscillations occur much more rapidly, they can in principle divide time into even finer parts. The technical challenge is formidable. To count such rapid cycles, physicists use devices such as optical frequency combs, which connect optical frequencies to measurable standards in a controlled way. With these tools, timekeeping reaches precision so high that tiny differences in gravitational potential across small height changes above Earth become measurable through general relativistic time dilation. A clock raised by a small vertical distance can tick at a detectably different rate. At this level, precision measurement joins relativity, quantum control, and metrology, the science of measurement, into one unified practice. This success reveals something striking. Physics can measure time differences with incredible accuracy, even though the concept of time itself remains unresolved at the deepest level. A clock can show that gravity alters rate. It can show that motion alters duration. It can synchronize global systems and test fundamental theories. But a clock still compares one process with another. It does not tell why there should be a parameter or structure called time beneath all such comparisons. The better the clocks become, the clearer this distinction appears. Precision answers many practical questions and intensifies the conceptual one. Quantum limits also enter the picture. At very high precision, measurement is never entirely free from quantum effects. The act of preparing and reading a clock involves systems that obey quantum rules. Noise cannot always be reduced arbitrarily. The uncertainty principle, which limits how precisely certain pairs of physical quantities can be known or prepared together, influences how stable and how readable some clock systems can become. Engineers and physicists develop methods such as entangled states and squeeze states to reduce particular forms of noise and improve performance. These methods use the very quantum features once seen mainly as obstacles. The microscopic world becomes both the source of the best clocks and the source of fundamental limits on how such clocks can behave. There is also a deeper conceptual tension. In ordinary quantum theory, time is treated as an external parameter used to describe the evolution of quantum states. Yet the clocks used to realize time are themselves quantum systems. This means the theory depends on time while the physical systems that instantiate time standards belong to the theory's own domain. The circle is workable in practice, but philosophically it remains incomplete. Physics uses clocks made of matter to measure time. While some of its best formal descriptions still take time as given from outside, the closer measurement moves to the quantum edge, the more visible this tension becomes. Experiments with ultra-precise clocks also turn clocks into probes of nature. They test whether fundamental constants remain stable over time, search for tiny departures from established theories, and measure relativistic effects in ever finer detail. A clock is no longer merely a passive recorder of duration. It becomes an instrument for examining the structure of physical law itself. When two clocks disagree after motion, altitude change, or exposure to different conditions, the disagreement is not nuisance alone, it is data about the world. Timekeeping at the frontier becomes an experimental language in which gravity, motion, quantum states, and field interactions can all speak. Yet none of this settles whether time is fundamental or emergent. The clocks function brilliantly regardless. This is one of the most revealing patterns in all of physics. A theory or device can work with extraordinary success while leaving interpretation incomplete. An optical clock can compare rates so finely that the shape of Earth's gravitational field becomes measurable through elapsed time. An atomic reference can define the second with astonishing consistency. Satellite systems can depend on these standards minute by minute. Still, the question remains, are these devices revealing a basic feature of reality called time? Or are they tracking relations among physical processes from which time itself somehow arises? The measurements alone do not decide. At the quantum edge, time becomes almost paradoxical in its role. It is counted more exactly than ever before, yet counted by processes whose own description invokes probabilities, decoherence, environmental control, and relativistic correction. The clock appears as one of the most concrete objects in science, and one of the most conceptually elusive. Its face, whether digital or abstract, suggests certainty. Its physical basis points toward layers of theory still not fully reconciled. The more exact the timing, the less simple the meaning. This inward region therefore reveals a quiet truth about modern physics. Mastery of measurement is not the same as mastery of interpretation. Atomic and optical clocks show that human beings can stabilize, compare, and exploit the most regular known processes with extraordinary skill. They make communication networks possible, refine navigation, test relativity, and strengthen the foundations of science itself. At the same time, they sit at the meeting point of unresolved ideas about quantum evolution, relativistic duration, and the status of time as a basic ingredient of theory. Physics can count time with unmatched precision. It still cannot say with full confidence what time ultimately is beneath the counting. At the deepest known frontier of theoretical physics, two great frameworks stand facing one another with unmatched success and unresolved tension. General relativity describes gravity, space-time, and the large-scale structure of the universe with extraordinary power. Quantum theory describes matter, radiation, and microscopic processes with equal success in its own domain. Each theory works where it is meant to work. Each has been tested again and again. Yet when physics tries to apply both together in the most extreme conditions, the union remains incomplete. In this region of the subject, the mystery of time reaches one of its sharpest forms. Time seems fundamental in one framework and strangely unstable, or even absent in another. The search for quantum gravity becomes, in part, a search for what time is when the deepest layers of law are forced together. General relativity treats time as part of space-time geometry. Clocks measure proper time along world lines, and gravity changes the structure through which those world lines pass. Time is not absolute, but it is real within the theory as part of the geometric fabric of the universe. Quantum theory, in its standard form, usually treats time differently. It often uses time as an external parameter against which the quantum state evolves. The state changes in time, but time itself is not generally promoted to a quantum variable in the same way as position or momentum. This difference becomes manageable in ordinary situations, where one can use relativity for large-scale structure and quantum theory for small-scale interactions without demanding a fully unified picture. It becomes much harder when the situation itself requires both descriptions at once. Such situations arise near black hole singularities, in the earliest moments of the observable universe, and wherever matter and energy are compressed enough that quantum effects of space-time itself are expected to matter. A singularity, in the language of general relativity, is a place where the mathematical description indicates that curvature becomes unbounded, and the ordinary theory breaks down. Most physicists do not take this to mean that nature literally contains an intelligible point of infinite density, described completely by current equations. Rather, it signals that the theory has reached the edge of its reliable domain. Something deeper is needed. That deeper account would have to combine gravity with quantum principles. In doing so, it would also have to say what happens to time when space-time geometry is no longer classical. One of the most famous expressions of this difficulty appears in the Wheeler-DeWitt equation, a candidate equation arising in some approaches to quantum gravity. In simplified form, it seems to describe the quantum state of the universe without an explicit time parameter of the familiar sort. This has led to what is often called the problem of time. If the deepest equation describing the universe lacks time in the ordinary sense, then how does the experienced world of change, sequence, and becoming arise? How do clocks, memories, motion, and cosmic history appear from a framework that looks timeless at its base? The challenge is profound because it does not concern one isolated technical puzzle. It concerns whether time is fundamental at all. Some approaches suggest that time may be emergent. Emergent means that a feature appears at larger scales from deeper ingredients that do not themselves contain it in the same obvious way. Temperature offers a familiar example from another part of physics. A single atom does not have temperature in the ordinary thermodynamic sense, but large collections of particles do. In a similar spirit, some physicists explore whether time might arise from relations, correlations, or coarse-grained descriptions of deeper quantum states. On this view, the world at the deepest level may not possess a universal flowing time, yet effective time could appear in the larger domains where clocks, observers, records, and thermodynamic arrows become meaningful. Other approaches keep a more basic role for time but redefine its status. In loop quantum gravity, space-time geometry itself is treated in a quantized manner, with discrete structures playing an important role in some formulations. In string theory, time often remains present, yet the theory introduces additional dimensions, dualities, and extended objects that complicate simple classical intuition. In holographic ideas, inspired by black hole thermodynamics and the study of quantum fields, space-time in some cases may be related to descriptions on lower dimensional boundaries. These frameworks differ greatly in method and interpretation. None has yet produced a complete, experimentally confirmed final theory of quantum gravity. Observations indicate that both general relativity and quantum theory remain extraordinarily accurate where tested. It remains uncertain which deeper route, if any now under study, will prove correct. Black holes sharpen the mystery. They combine strong gravity, horizons, thermodynamics, and quantum effects in one setting. A black hole has entropy and temperature in a precise theoretical sense, especially through the work linking black hole mechanics with quantum field theory and curved spacetime. This is already striking, because it ties geometry, information, and thermodynamic time together in an extreme environment. The black hole information problem then asks how information about matter falling into a black hole is treated when the hole emits radiation and may eventually evaporate. If information is truly lost, quantum theory faces strain. If information is preserved, the mechanism must be subtle. Time enters this problem at every level, through evaporation, causal structure, horizons, and the relation between earlier states and later radiation. The issue remains one of the deepest in theoretical physics. Cosmology brings the same tension to the whole universe. The early universe is dense, hot, and shaped by conditions where both quantum effects and space-time curvature matter. Standard cosmology describes a great deal successfully, including expansion, background radiation, and structure formation. Yet the very earliest regime, where quantum gravity effects are expected to dominate, remains uncertain. Physics can trace cosmic history back to extremely early times with growing confidence. It cannot yet provide a complete and confirmed account of the deepest beginning. Without that account, the status of time near the origin of the observable universe remains unresolved. Did time begin in a meaningful physical sense? Does the question itself break down under a deeper theory? Present knowledge does not settle the matter. The problem of time therefore reaches beneath clocks and equations into the architecture of theory itself. If time is fundamental, then physics must explain how it fits consistently into both gravitation and quantum law. If time is emergent, then physics must explain how the felt and measured world of temporal order arises from something more basic that is not temporal in the familiar sense. Either path is difficult, a timeless foundation risks making change hard to recover. A fundamental time risks conflicting with the lessons of relativity and the formal structure of quantum gravity candidates. The mystery does not shrink at this depth, it becomes more exact. In this inward region, physics stands at a threshold. The outer universe shows expansion, light shows layered pasts, clocks measure intervals, relativity bends duration, entropy gives direction, records preserve what has been. Quantum theory governs microscopic possibility, but here, where the deepest frameworks must meet, time itself becomes questionable in status. It may be geometry, parameter, relation, emergent order, or something not yet properly named. The search for quantum gravity is therefore not only a search for one more equation, it is a search for the level at which time either survives as basic reality or gives way to a deeper structure from which reality as timed experience somehow emerges. At the innermost point of the inquiry, the question becomes quieter and more difficult at the same time. After the sky, the stars, the clocks, the equations, the curved geometry, the arrow of entropy, the persistence of records, and the instability introduced by quantum theory, physics arrives not at a final answer, but at a boundary of competing possibilities. Time remains central to nearly every successful description of nature, yet its status is still unsettled. In this deepest region, the task is no longer to show how time is measured or how it behaves under known laws. The task is to ask what kind of thing time is, if it is anything in its own right at all. Physics still cannot solve this mystery, because each path inward reveals genuine structure while leaving the foundation incomplete. One possibility is that time is fundamental. On this view, time belongs to the basic architecture of reality. It is not made from anything else. Events occur in succession because succession is part of the world at its deepest level. Clocks work because they track something real and primitive. Change is possible because time is there for change to unfold within it. This idea retains much of ordinary intuition, while discarding the old classical requirement that time flow identically everywhere. Time could be fundamental without being absolute in Newton's sense. It could still vary with motion and gravity, as relativity shows, while remaining part of the basic structure. The appeal of this view is its directness. It respects the fact that physics needs temporal order almost everywhere, and that experience is saturated with passage, memory, and becoming. Yet the fundamental view faces pressure from deeper theory. If some candidate descriptions of the universe work without a clear time parameter, or if the most basic laws appear more naturally in relational or timeless form, then time may not sit at the foundation after all. This leads to the second major possibility, that time is emergent. In that picture, time appears only at larger scales or under particular conditions. Much as temperature appears in large collections of particles, though not in the same way for a single particle alone, the basic reality might consist of relations, quantum states, informational structures, or causal patterns from which time arises when the system is described in a coarse-grained way. A clock would then not reveal a primitive ingredient called time so much as participate in an effective structure that becomes valid in the macroscopic world. The emergent view has real strength. It helps make sense of why the deepest equations in some approaches seem not to contain familiar time. It also fits the way thermodynamic direction, records, and classical definiteness appear to grow out of more basic layers. The familiar world of before and after may be a large-scale achievement rather than a microscopic given. Still, emergence brings its own burden. If time is not basic, then the theory must explain how real sequence appears so robustly. It must explain why conscious beings experience passage, why clocks agree enough to support science, why records point backward, and why the world does not feel like a timeless mathematical object from within. To say that time emerges is not yet to show how it emerges. A third line of thought treats time as relational. In this approach, time is not an independent substance or background. It is a way of describing change among physical systems. One system acts as a clock relative to another. Duration is not something flowing by itself, but a measure of correlation between processes. This idea has deep roots and continues to influence modern work. It aligns with the practical fact that clocks always compare one process with another. It also fits some aspects of relativity, where local times belong to paths and relations rather than to a single global stream. A relational view can reduce the temptation to imagine time as an invisible thing, moving independently of the world. The world changes, and temporal structure is abstracted from that change. Still, a purely relational account may feel incomplete. If all time is reduced to relations among events, one may still ask why those relations have the asymmetry they do, why some relations are remembered and others anticipated, and why a sequence of correlations should feel like passage rather than like a static pattern. The problem may shift from time itself to the structure of relation, but it does not automatically disappear. Physics can describe correlations with impressive power. The deeper meaning of succession can remain elusive even there. Another possibility is that present theories are simply incomplete in ways not yet visible. This is a sober and often necessary position. Science advances not only by refining old concepts, but by discovering that some of them were framed too narrowly from the start. Time may be one of those concepts. The familiar alternatives of fundamental, emergent, or relational may not exhaust the truth. A future theory could preserve parts of each while changing their meaning. It could show that time is fundamental in some respects, emergent in others, and relational in practice. It could reveal that the conflict between relativity and quantum theory points not to the elimination of time, but to a more subtle form of temporal structure not yet clearly imagined. Observations indicate that existing theories capture real aspects of nature with extraordinary success. It remains uncertain how those aspects fit into one complete picture. What is known is substantial. Physics knows that clocks do not all run alike. Motion and gravity alter elapsed duration. The universe has a thermal history and a finite age in the ordinary cosmological sense of the observable expansion history. Light brings information from earlier states across vast distances. Entropy gives macroscopic processes a direction. Records preserve the past in matter, radiation, and mind. Quantum theory predicts microscopic behavior with immense accuracy, while leaving the status of measurement and temporal definiteness contested. None of this is vague. The mystery of time does not survive because science knows nothing. It survives because science knows so much in pieces that do not yet rest together without strain. What remains uncertain is equally important. It remains uncertain whether passage belongs to the world itself or to the way conscious systems register ordered change. It remains uncertain whether the arrow of time can be fully reduced to boundary conditions and statistical law, or whether a deeper temporal asymmetry exists in nature. It remains uncertain whether space-time is fundamental or emergent from underlying quantum structure. It remains uncertain how to unite gravitation and quantum theory without either losing time or misunderstanding it. These uncertainties are not signs of failure in the ordinary sense. They are the live edges of understanding. At the deepest inward layer, physics therefore reaches a kind of disciplined humility. It can time spacecraft, compare atomic transitions, detect gravitational waves, reconstruct cosmic history, and predict experiments with astonishing fidelity. Yet when it turns inward and asks what time itself is, it still finds no consensus strong enough to close the question. Time may be the framework of change, the product of change, the order of relation, or a provisional concept awaiting revision. For now, the mystery remains. Physics still cannot solve it, not because time is absent from nature, but because time is present in so many successful descriptions without yielding one final meaning beneath them all. The inquiry comes to rest in the same quiet place where it begins, with change unfolding and no final definition beneath it. The universe expands. Light crosses darkness, carrying earlier worlds within it. Planets turn, clocks count, and bodies age. Gravity stretches duration. Motion separates one measured history from another. Heat drifts toward balance. Records gather behind each passing event. At the smallest scales, probability enters. At the deepest theoretical edge, time itself seems to blur, sometimes appearing fundamental, sometimes emergent, sometimes only relational. Physics follows all of these signs with patience and precision. It measures, compares, predicts, and tests. Again and again, it finds lawful structure. Again and again, it stops just short of the final answer. This does not make the effort empty. It gives the mystery its true shape. Time is not hidden because nature is silent. Nature speaks through clocks, stars, atoms, entropy, memory, and geometry. The difficulty lies elsewhere. Each of these reveals a real aspect of temporal order, yet none alone explains why there is an order to reveal. The world offers duration without a final account of what duration is. It offers sequence without full agreement on the meaning of sequence. It offers a strong direction in experience and process, while theory still debates whether that direction is basic or derived. So the subject settles into uncertainty without confusion. Much is known, much remains unresolved. The oldest human sense of passing time survives, but it now lives beside expansion, relativity, quantum law, and thermodynamic arrows. Physics does not close the mystery. It makes it clearer, calmer, and deeper. In that calm, time remains what it has always been in science, measurable everywhere, central to everything, and still not fully understood.